Good morning to all of you students. Today I am going to explain about the queue data structure. Queue data structure is equally important like other data structures that we have discussed earlier like stack data structure. So the basic concept of the queue is this is for FCFS system. This is first come first serve system, or it uses the concept of FIFO. This is first in first out system. If we talk about the real life, we see so many queues at so many places like bus stand, railway stand, etc. If we talk about the computer science, it can be used in various situations like for scheduling in operating system. It can also be used in printer. It can also be used in customer care service center applications. So this video basically covers the definition of the queue, implementation of the queue by using the array and linked list, and some applications of the queue and the limitations of the queue. So let us see what is queue. So in simple terms, a queue is a line of persons waiting for their turn at some service counter window. A service counter can be a ticket window of a cinema hall, it can be a bus station, it can be a railway station, or it can be a bank that we normally see in our daily life, such type of situations. And there could be a queue of varying lengths. There may be so many queues of different lengths. Means it may contain 10%, it may contain 5%, it may also contain 100%. It depends on the type of the service provided by the service counter and the number of persons the service. But the one thing which is common in all type of queues that we normally see in the real life situations, the service at service counter is provided on the first come first serve basis. This is FCFS basis. So I would like to say that the main concept of the queue data structure, this is FCFS, or it uses the concept of FIFO. This is first in first out system. That is to say in order of their arrival in the queue. Now we will see the definition of the queue. In the context of the data structure, a queue is a linear list in which the insertion can take place at one end, and this one end is called the rear of the list, and the deletion can take place at the other end, and this is called the front of the list. And the behavior of the queue is like this is first in first out system or the FIFO system. If the terminology in the queue data structure, the insertion and deletion operations are known as NQ and DQ operations respectively. Moreover, it can also be defined as in a queue all operations take at one place at the end of the queue or the other. The NQ operation adds an item to the back of the queue, and the DQ operation removes the item at the front of the queue. We can see in this diagram like this is the front. We are having 5 elements in this queue like 46, 125, 8, 22, 17. This end is known as the front end. We can delete the element from here, and this is the rear end, and we can insert the element at here. So this is after DQ operation, means we have deleted this 46 from this queue. So this is the resulting queue after DQ operation, and in this here we have inserted 83 at the rear end. So this is NQ operation. Plus the operations on the queue data structure. This is the first operation. This is create queue. This is used to create an empty queue. And the second operation is this is NQ operation. This is used to insert an element in the queue. As we know, the element can be inserted at the rear position. In the DQ operation, this is the third operation. This is used to delete an element, and the element can be deleted from the front position. Peek function. This is used to access the first element of the queue without removing it. And then fifth function, this is full. This is a boolean function, and it can be used to check whether the queue is full or not. It returns two type of values. This is true and false. Sixth function is is empty. This is also Boolean function. This is used to check whether the queue is empty or not. Is full is normally used before inserting the element in the queue, and is empty is normally used to whenever we want to delete the element. So before deletion the element, we must use the is empty. It is to be noted here that all operations runs in order of one time, or we can say the time complexity of the queue data structure. This is order 1, and if the queue is empty, then it is not possible to delete the element, or it is not possible to dequeue the queue, and the peak operation is also not valid. Therefore, we must ensure that the queue is not empty before attempting to perform these operations. Likewise, if the queue is full, then it is not possible to enqueue a new element into the queue. Therefore, we must ensure that the queue is not full before attempting to perform enqueue operation. Now, we will see the queue representation in memory. Queues, like other data structures like stack, can also be presented in memory by using either we can use a array, linear array, or we can use the linked list. This is static memory allocation, as we know, and this is dynamic memory allocation. Moreover, even using a linear list, further we have two implementations of queue, that is linear and circular. So we can use linear queue, or sometimes we use the circular queue. The representation of these two is same. The only difference is in their behavior. That like we will discuss the circular queue later, and we will see the difference between the linear queue and the circular queue. Normally, a linear queue and the circular queue both are same, but logically they are different. Now, first we will see the first category of queue, that is representing a queue using array. To implement a queue using array, we need two variables called front and rear. As we know, there are two important points in the two important ends in the queue data structure, that is the front and the rear. So we need two variables, front and rear, that hold the index of the first and last element of the queue, and the array to hold the element of the queue. This is the structure that we can use in the coding to create a queue. Now with the above declaration, queue of 10 elements can be represented in memory as shown below. This is figure A. This is for representation of empty queue in memory. Here we are having 10 locations because we are using the array. So this is static memory allocation. In this we will use two variables. This is front and rear. In the starting, when this is empty queue, so the value of front and rear will be -1. Front is -1, rear is also -1 because this is the empty queue. Now this is the second figure after enqueuing some elements. So this is the representation of queue in memory after enqueuing elements, after inserting elements like 5, 7, 12, 8 and 9. So these are the positions of the 5 elements. First we will insert the 5 and then 7, then 12 and then 8 and then 9. That's why the position of this front element is 0, and the position of this element is rear element is this is 4. Now this is figure C, or we can say this is another situation when we are having three elements in this queue. This is 12, 8 and 9. These two elements are deleted. So in this situation, the value of front is 2. This value of front is 2, and the value of rear is this is 4. Now this is figure D. This is the representation of queue in memory after enqueuing elements 12, 8, 9, 3, 10, 11. So here the value of front is 2, and the value of rear is this is 7. This is 7, this is 11 at this 7th position, and this is 12 at second position. This is another figure in which we are having some elements, and the front is this is 2, and the rear is this is 9. So we are having 8 elements: 12, 8, 9, 3, 10, 11, 15, 20. Now in this figure, there is an important thing that it is not possible to enqueue more elements, though we are having two positions lying vacant. As such, the two positions in the linear queue are vacant. Now, to overcome this problem, the elements of the queue, they are to be moved forward so that the vacant position are shifted towards the rear end of the linear queue. So after shifting front and rear are adjusted properly, and then the element is enqueued in the linear queue as usual. Difficulty when the two positions or some positions are lying vacant in the front, but the last position is filled. So we can treat this, or this difficulty can be removed if we treat the queue position with the index 0 as a position that comes after the position with the index 9. That is, we can treat this as a circular queue. This circular queue is also called the ring buffer. So in this diagram we can see that the linear queue is treated as a circular queue. So this is the representation of empty queue in memory. We are taking the same example. So this is empty queue, and if we are treating this as circular queue, this is front and the rear. Implementation of operation using array. Creating empty linear queue. Before we can use queue, it must be created or initialized. The purpose of initializing the queue is served by assigning value -1 to the front and rear variables. The initialization of queue can be done with the following function. We can use this following function. Here we are assigning the two variables to -1. This is front and rear equals to -1. Before removing an element from a queue, it is necessary to test whether a queue is empty or not, and this is known as the condition of underflow. If the queue is empty, then the delete operation or the dequeue operation cannot be performed, and it can be performed by comparing the value of front with -1. Like here we can see this in this code. So this underflow condition is very important, and this function is a boolean function. If it returns true, it means we cannot delete the element in the queue. If it returns false, it means we can delete the element. It means there is some element in the queue. Before inserting an element into a queue, it is necessary to test whether a queue is already full or not. If the queue is full, then the in-queue operation or the insertion cannot be performed, means we are unable to insert the element at rear position. This can be performed by comparing the value of rear with -1 and front with 0, or by checking front equals to rear plus 1. This we can see here in the code like this and this. So this is full. This is a boolean function. If it returns true, it means the queue is full and we are unable to insert the element. If it returns false, it means we are able to insert more elements. The fourth operation, insert operation or NQ operation on linear queue. Even if a linear queue is not full, there is another problem that may arise during NQ operation when the value of the rear is equal to capacity -1 or the maximum value. So the value of front variable is not equals to 0. And this possibility implies that the incoming element cannot be enqueued. It cannot be enqueued unless the elements are moved forward and the variable are adjusted accordingly. So there are two conditions which can occur even if the queue is not full. So this is important situation in the queue data structure, and it can occur even if the queue is not full. If a linear queue is empty, then the value of the front and rear variables will be nil. Then both rear and front are set to be 0. If a linear queue is not empty, then are further two possibilities. If the value of the rear variable is less than capacity minus 1, then the rear variable is incremented. And if the value of the rear variable is less than capacity minus 1, then the elements of the linear queue are moved forward and the front rear variables are adjusted accordingly. So this is the algorithm for NQ operation. If rear equals to size, then queue is full. Then we need to print queue is full, exit else. If front equals to 0 and rear equals to 0, then queue is empty. And then set front equals to 1. So these are the two important points, steps we can say, when the queue is full and when the queue is empty. Code for the NQ operation. Another operation, this is the delete operation, the dequeue operation on the linear queue. Before performing the delete operation, we need to check the condition of underflow. If the condition of the underflow is if the condition of the underflow is true, then we are not able to perform the dequeue operation. So the front element of the linear queue is assigned to a local variable, which later on will be returned via return statement. After assigning the front element of the linear queue to local variable, the value of the front variable is modified. So there are two possibilities. If there was only one element in a linear queue, then after dequeue operation, queue will become empty. This state of linear queue is reflected by setting front and rear variables to -1. Otherwise, the value of the front variable is incremented. So this is the dequeue operation algorithm. If front equals to 0, then print queue is empty, and then exit else item equals to queue front. If front equals to rear, then rear equals to 0 and front equals to 0. So we need to set these rear and front 0, else front equals to front plus 1. So this is the algorithm of deletion operation in the queue. By this code, this is the code for the dequeue operation. This is sixth operation. This is accessing front element without deleting. The front element can be accessed by the following function. This is peek. Obviously, there are some limitations on the linear queue. The only limitation of linear queue is that if the last position of the queue is occupied, it is not possible to enhance any more elements even though some positions are vacant toward the front position of the queue. However, this limitation can be overcome by moving the elements forward such that the first element of the queue goes to the position with index 0 and rest of the elements move accordingly. And finally, the front and rear variables are adjusted appropriately. So this operation is time consuming. So we can see here that the operation is the time consuming if the length of the linear queue is long. So this limitation can be overcome. It is better to use a circular queue rather. So this limitation can be overcome if we treat the queue position with the index 0. It comes immediately after the last queue with index capacity -1. So the resulting queue is known as this is circular queue. Second category of implementing a queue, we can use a linked list to implement this queue. A queue represent using linked list is this is also known as linked queue. The array-based representation of queue suffer from some limitations. Some limitations are there if we implement the queue by using the array. Like this, size of the queue must be known in advance because this is the static allocation. And we may come across situations when attempt to enqueue an element may cause overflow. However, the queue as an abstract data structure, it cannot be full. Abstractly, it is always possible to enqueue an element in a queue. Therefore, implementing a queue as an array provides the growth of queue beyond the finite number of elements. So these are the limitations of the array. If we implement the queue by using the array, that's why we use linked list. So this is the code. If we use the linked list, in this figure A, we can see the implementation of the queue by using the linked list, that we are having two variables. This is front and rear. This is a node, and this pointer is indicating to this node. We are having 5 elements: 5, 7, 12, 8, and 9. So this is the representation of queue in memory using linked list after enqueuing elements 5, 7, 12, 8, and 9. As we know, in linked list there are two variables. First is used to store the info, and this is the pointer variable. It can be used to give the address of another node. Figure B, this is the representation of queue in memory using the linked list after enqueuing 3 elements. This is 12, 8, and 9. And this is figure C, representation of queue in memory using linked list after enqueuing elements 12, 8, 9, 3, 10, 11. Now we will see the operations one by one. Implementation of operations on linear queue using the linked list. This is first operation, means we need to create an empty queue like we were doing in the case of array. So before using a queue must be created or initialized. To initialize a queue, empty linked list is created by setting the pointers variables front and rear to null. Earlier in case of array we were using -1, but here we will assign front and rear to null because we are using the pointers. This is testing queue for underflow. As we were doing in the case of array, we will check before the delete operation, before dequeue operation, we will go for the to check the underflow condition. The queue is tested for underflow condition by checking whether the linked list is empty. The empty status of the linked list will be indicated by the null value of the pointer variable front. So this is the code. Queue for overflow. Since a queue is represented using a linked list and it can grow to a limit of computer's memory, therefore overflow condition never occurs. Hence this operation is not valid or implemented for linked queue. Applications. So there are some applications. But this first application is CPU scheduling or the disk scheduling. When multiple processes require CPU at the same time, various various CPU scheduling algorithms are used, which are implemented using queue data structure. And the second application is when data is transferred asynchronously between two processes. Here also queue is used for synchronization. For example, IO buffers, pipes, file IO, etc. It can also be used in print spooling. Documents are loaded into a buffer and then printer pulls them off the buffer at its own rate. Fourth application, this is breadth first search in a graph. It is an algorithm for traversing or searching graph data structure. This is also known as BFS. It starts at some arbitrary node of graph and explores the neighbor nodes first before moving to the next level neighbors. This is very important concept in the graph data structure, and this uses the concept of queue data structure. Fifth one is handling of interrupts in real-time systems. Most of the interrupts, they are handled in the same order as they arrive in FCFS order, and it uses the queue. And this is very popular algorithm. This is round robin scheduling technique. It also uses the queue, and moreover, The last, all types of customer service centers like railway reservation, air ticket reservation, and various type of reservation, they also use the concept of the queue at the back end. Limitations or issues of the queue data structure, definitely there are some issues in the queue data structure. You cannot use queue for LIFO operation, nor you can use store hierarchical data in it. This is the first limitation. And the queue are implemented in two ways, using arrays and using linked list. Array implementation has space limitation and hence limited capacity. If we use the array to implement the queue, then it suffers the space limitation because it has the limited capacity. And the fourth one is linked list implementation solves this problem, but it is we can use linked list for the implementation, and almost it solves the problem, but it becomes the slow. So these are the limitations. As in this video lecture, we have seen that what is the queue data structure and how it can be used, what are the different operations so which are associated with the queue data structure, how it can be implemented. Like there are two ways, we can either use the array or we can also use the linked list to implement this. There are some applications, there are so many applications we have seen, and there are limitations too. So thank you very much.